we need to move on. I think this is often a whirlwind kind of aspect of FPTalks, but it means we get exposed to a lot of ideas per hour. So our next speaker is Ben Sherman. Ben was until somewhat recently at MIT, where he finished a computer science PhD with Mike Carbon. So he'll be talking about some of that work, which has continued a bit.
All right, thanks, Pavel. So I basically just want to show everyone like a fancy calculator that I made during my PhD. So hopefully this should be showing up.
Yep.
Cool. So it's like an embedded language within Haskell. So I'll just load it in and we can start playing at the REPL basically. It's also, I did not build out any syntax. So some syntax things will be awkward and I'll point that out. But the basic principle is that everything in the language is a real number expression, like it means something that's a real number. And so when you want to look at it and you look at the answer, you just give it a precision to evaluate it to. So here what I'm saying is, let's evaluate square root of 2. Let me just clean this up a little bit. Let's evaluate the square root of 2 to 2 decimals of precision. Basically get me an answer within 1/100th. So it gives me an interval with a lower bound and an upper bound. And the guarantee, right, is that the true answer is between those bounds and that the bounds are going to be as tight as I requested. So the difference between the upper bound and the lower bound is 0.01. And so the nice thing about this is I can go back and I can get, since it's a real valued expression, I can get as many digits of precision as I want. Okay, cool. So that was square root of 2. Now you could imagine, right? We have our built-ins of like numbers, 2, square root. But how do you define square roots anyway? Well, the way you may remember, like, what is a square root? It's the thing that's such that if you square it, you get 2. So for square root of 2. Right? And that actually gives you a method of computing it. It's like essentially just try to find the thing that's such that when you square it is 2. So that's like a root finding problem. And we know Newton's method is a popular and very efficient method for doing root finding. And so in this language, every expression is actually infinitely differentiable by default. And so we can create a new square root function. I'm going to do it right here. So I'm going to use this built-in function, which is a higher order function called cut root with bounds, which is just do Newton's method. So it says do Newton's method. I want some number between 0 and x. I know the square root of x is between 0 and x. And then I'm going to say, well, of what function? Root finding of what function? So find some function when it's equal to 0. And so what I'll just do is x minus y squared. So I'm just saying, find the y such that when I square it and subtract x, or subtract it from x, I get 0. So there's my definition. And now I can do that same thing that I did before with square root of 2, but I can use my square root of 2 function, and let's not go crazy here. And so I can compute square root of 2 like this. So the fun thing there is it's digging into that expression of x minus y squared, and it's computing a derivative to use Newton's method to get an answer that's fairly precise, and it propagates all those bounds within the language. So as I said, everything in the language is infinitely differentiable, which means there's a derivative operator just in the language, and I can use that on my square root method. So let's evaluate something's 2 digits of precision. Oh, and feel free to like jump in and ask questions live or ask me to compute something live. So let's do the derivative of my square root operator at 1. So we might remember from your calculus class, like this is like 1 divided by 2 square root x. And so at 1, it should be 1/2. And we see actually, it turns out here we get infinite precision. Here we get exactly, yes, the answer is 1/2. So you might wonder, like, Newton's method uses the value in the first derivative to get a value. right? But then how do we get the derivative of something computed using Newton's method, or the derivative of an expression that was computed using root finding? Well, this is just something from our calculus class. The implicit function theorem tells us exactly this, the derivative of an expression that was constructed using root finding. And that's built into that operator that we have, that root finding method. It's essentially everything in the language isn't just continuous, such that we can kind of get arbitrary precision. It's also smooth, such that we can take derivatives. And the higher order functions let us do these derivatives. So just to confirm that we can do this, we can even get the second derivative here. So just for the sake of time, I'm going to copy and paste and do this here. Now I'm just going to check questions. Is the requested accuracy absolute or relative? It's absolute. And so if everything is differentiable, there are no if statements or partial functions, or is there some weak derivative in use? So yeah, a lot of the paper that I have that's like related to this is about the handling of some of this partiality of like having things that are like continuous, but like only, differentiable, like not at a corner, but maybe it's like there's an interval derivative if it's a Lipschitz. So there is handling of that, but I don't want to focus on it because those are the not nice bits. And then like you just sort of pay a lot of attention to how not nice things get as you continue to take derivatives on stuff. So I'm going to just like stay in the smooth land for this talk. Cool. So we do the second derivative. It's -1/4, which maps with what I remember doing things symbolically in my calculus class. Nothing symbolic is happening here. It's really all sort of like more computational. All right, so I have an integral 0, 1 function built in that's doing like Riemannian integration, and that's a smooth operator too. It's a little inconvenient to have integral 0, 1, so I can build out a function that does an integral from a to b. And so I just have this up here, this my integral function, right? And it's just like use that integral 0 to 1, but like smush the inputs and go between a and b, and then multiply the result by b minus a. So we can use that, and I can do things like using cosine, I can define sine. So I'll just do that. Oops. Here, so sine is the integral of cosine, right? So I can just do this. I'm saying integrate from 0 up to z, the function cosine x. And so let's just compute that we can do this. So sine of pi over 2, that should be 1, if I remember correctly. So I do it. Sine of pi over 2 should be okay. I must have done something wrong. Can't figure it out here. Let's see, just check questions. What happens when you divide by 0? Good question. Let's see. Oops. Oops. You get an infinite loop. It just keeps trying to compute, because the thing is, if you do something divided by like this, right? Well, it's very quick, but it's sort of slow. It's very close to 0, and it is a legitimate answer. So it keeps trying to refine that 0 number, and it's an infinite loop. You could cut off here because it's like possible, but in general, it's uncomputable to cut off. So I just let it do the in general thing, which is an infinite loop. You can even do things like maximization. So there's a maximization operator in the language. So I can say, find the maximum value of this expression, choosing x's over 0 and 1 to like get this perimeter. I chose an expression that has a max of 1. And you can do argmaxes too, because argmaxes are just root finding, right, of smooth expressions. So I can say that where does the argmax occur of this thing? It happens at 0.5. So I'll just end off with like, this isn't super interesting, but it's like, take the derivative of the integral of a thing with like sine and cosine and log. And it's just one of these fun first examples that I found where like Wolfram alpha just completely barfs on this. It doesn't produce anything useful, but we can get an answer pretty quickly. So again, it's just kind of computing things through, but it's this language where all the operations kind of not only have like arbitrary precision calculation information, but smooth like all their derivatives, and it just all plays together nicely. So I didn't get into the time to say exactly how this works, but there is a paper which I should probably computable semantics for whatever.
We'll post it on the website.
Yeah.
Papers
cool.
will be linked from the FPTalks website.
All right, so let's see. Let me just check the questions again. Does the argmax operator find the global maximum or just a local maximum? So argmax is finding a global maximum. So what it first does basically, if I remember correctly, and you could implement it a few different ways, is it kind of checks all the intervals to see basically to find the thing that has the global max, and then it kicks off the root finding for the argmax. So if you have something where the argmax is not unique, you'll get an infinite loop.
Cool. And there's also a question from Paul Zimmerman. I don't know, Paul, do you want to ask it in person?
Yes. So my first question is my first question is what is underlying arithmetic package?
Basically MPFR, if I remember correctly. So I'm using a lot of operations from MPFR, and the implementation of sort of arbitrary precision floating point values, I think also comes from MPFR.
Okay. And when you ask a 2 digits precision, is it absolute or relative precision?
Absolute.
Okay. Thank you.
Okay, great. I think there's also a question in the channel from me, so why don't I just ask it directly? Oh, okay. Maybe I shouldn't take it up. There's a question from Benjamin Valby. Do you want to ask that in person? Maybe not. All right. So Benjamin asked. Oh,
there's a question in there.
Yeah.
I'm happy to just answer it. Yes,
Great.
it will give. The only thing it needs to do is give type bounds at least as tight as needed. So if we do, I think, was this the question? It gets actually infinitely precise answer, right? The difference between the bounds is 0 in that case. So of course that can only happen for rational numbers. Okay, so Sam asked, how is this different from Titanic, the FP core evaluator? Is there any MPFR under the hood? So yes, there is MPFR under the hood for a lot of the basic arithmetic. And I do not know what Titanic is.
I have a question. So there's some, when you say square root, the built-in one, not the one that you defined, or division, are those directly calling out to MPFR operators, or are those implemented as root finding as well?
Yeah, so the square root that I have built in is based on MPFR, which should be like the fastest version of that. It should be faster probably than this thing that's gonna like go through this language and use the root finding operator.
Cool. Okay, well, I think we're done just a minute or two ahead of time, which is perfect. The next thing up on our schedule is to take a half-hour break. But before we do that, I have a short announcement. Ben, do you think I can steal your steal your screen share? Yeah, so before we move into the break, I have